Hello, welcome back. So this is the second lecture about chapter 22 graph. In this lecture, we are going to take a look at our first simple graph class definition and its application. Okay, so the example is Java simple graph example. And there are four files: vertex, edge, the simple graph, and the drive. Okay, so first let's take a look at the vertex class definition. So we have an ID for vertex. We also have a string label for vertex. Okay, and we have the number of vertex and visited or not, and a vertex flag definition. And that's so that a vertex flag is an enumeration, okay, and it's not going to be used in this example, but this is going to be useful for our future more complicated cases, okay. So we identify vertex as unvisited, in progress, and done using enumeration. And for the vertex, the constructor, it's pretty straightforward, just assign ID label, okay. And we also provided toString for the output of the vertex and also identify if two vertex are the same, and also find the hash code. Okay, that's about the vertex. And for the edge class, it has two vertex, U and V, okay? And the constructor and the output the vertex using its two edges, and the equal as the same as user and the hash code. Okay, the major file in this example is the simple graph. Okay, so for our simple graph, so for all vertices, we use a map to represent. Okay, so we use the edge adjacency list. Edge adjacency list. Okay, and so for each vertex, we have a list of the edge, okay, that's associated with this vertex. So using this key value pair. So this is the key, and this is the value part, okay? And for the default constructor, pretty straightforward, just create an empty hash map. So here we use a hash map, okay, not a tree map, because no sorting is needed, but we want to maintain the uniqueness for all of the vertices. And the next method in this class is about agent to determine if two vertex are connected with an edge. Okay, so what we can do is we first need to check if vertex are in the map. Okay, so contains. If not, then definitely return false. Is it? If it is, okay, for the vertex, the get you, so this will return the edge list, okay. And then we use functional programming here to see, okay, for this, for its edge, okay, we are going to go through its edge one by one. So for each edge, then we try to see if it's the next vertex, the next node, okay, is the same as the other specified. So here we use U as a key, and then we try to find its v part. Okay, so if the count is not 0, then that means, yeah, they are adjacent. Is it? Yeah. And so this is a case for UV is the edge from U and V, okay? And all over here is we check, is it? So because maybe V is starting and the ending is U, is it? Something like that. Then we are going to see if it's count also not 0, okay? So we check both cases, VU and UV, okay? So this is for adjacency. And what next we did is we find a specified vertex U all of its neighbors and store it in a set. Okay. So here for this set, we call it a neighbor set. It's a hash set because no order needed. We don't need a tree set. Okay. So first we need to see if this U is in our vertex. Okay. If it is, okay, then we try to find its edge adjacency list, okay. For edge adjacency list, then we find the V. Once we find the V, we can add it to the set, okay. So we add all the other vertices from the edge UV here. And then for this case, since this is U is the key, is it? Then it's an edge list of the edge list. And so this may be like you have then the edge list. So A, B, A, D, something like A, C is it of the edge list, okay? And there may be another case, is it? So we try to get off the vertices and loop through it, okay? And try to, for each of the vertices, we try to see if the other end is U, is it? So any like B, D, and C, is it? To see if the other end is A, is it? So we need to consider both of the cases here. Okay, so that's about this neighbor. And for add vertex, it's pretty straightforward. You just call maps put if absent. You add this vertex and empty every list. Okay. And for remove vertex, okay, we first need to see if this vertex see if it has the edge list, okay. If it has the edge list, then we remove U, okay, for all these UV links, okay, we remove it. So this is to remove from the map, okay. Okay, and then we are going to loop through all the vertices. And for each vertex, okay, and we try to see its edge and see the edge's other end if it is a vertex U, okay. If it is, then we need to remove the edge, okay. So here is to remove all the edge. Okay, so that's about remove vertex. So remove vertex, you not just remove from map, you also need to think about remove the respected connected edge. Okay, and then for add edge. okay, add edge. So we specify two vertex, okay. And then first we need to see if the vertex U is already in the map. Okay, if it is in the map, then we find all of its edge. Okay, and then find if the edges at the end is this other vertex. If it is, that means this edge already exists. We don't need to do anything, okay? If it is not, then you create a new edge. Then you add this new edge to that array list. Okay, so if the vertex doesn't contain vertex U, is it? So we need to create an edge and then add a new array list first to this map, the vertices map, okay, and then you add this new edge to the respective array list here. That's how we add edge. So different scenario we need to consider, okay. And then we also have remove edge, okay. So you first, from the map, with respect to one of the vertex, you get the array list of the edges, okay? And here we use another edge variable, try to do something, okay? And so if this array list is not empty, then you're going to loop through the array list, okay? Then try to find the specific edge. Once you find it, you keep it here, okay? After we keep it, then we can remove it, okay? And then after we remove, because this you're going to remove from that array list, is it? Then we need update. So this is to update the map. The map is the vertex and its associated edge list. So we also need to do updating. So this is to remove edge. And then we also have a method to get all the vertices. We use a set, okay, to get it. Okay, so that's about the SimpleGraph class. And then let's take a look at the application. So in this application, what we first do is we first create a friendship graph. Okay, so we have A, B, C, D, E, six person, okay, and then we have the list of their friend, okay. So if there's a friend relationship, we create an edge. So what we do is we create the first graph G1, okay. Then we also needed to create all of the vertices. So over here, we create all of the vertices with their ID and the label, okay? And what next we did is we are going to add all of the vertices to the graph. And then we add all of the respective relationship, friendship, okay, to the graph. So we call add edge to add all of them. And after we create that, then we can output our graph, okay? And if you go back yeah, because for our graph class, we do have the output, okay, for our whole graph. So get each of the vertices, okay, and to output their corresponding relationship. Okay, and after this, then we check if B and D has a friendship, and also B is friend. Okay. And we can take a look at the output. So here is the original output. So graph GY is it? So node and all of its related edges. Yeah, edges. So A, B, A, C, A, D is it? So describe the relationship. So B and D, the relationship, let's see. Okay, B, and we have BA, BC. Yeah, we do have BD. Yeah, so they are. And then you can also see D, is it? And D and B. Yeah, so they are relation. They are neighbors, is it? So B's neighbor, it's we have A, we have C, we have D, we have E. So A, C, D, E. Yeah, that's correct. Is it? And what next we did is we try to remove edge BC. And after removing B and C, let's see what the graph is, okay? Probably let's also reference the previous one, okay? So that we remove B and C, that so BC should be removed. So then same thing, C and B should be removed. Is it? So then let's see. Okay, any updates? So A, not a change. For B, yeah, if you take a closer look, yeah, it's correct. C, yeah, it's no of the others, so no updates. So yeah, so that's correct. And then what next we did is then we also check B and D if the relationship is using the agents, and then find B's neighbor, and then all of the vertices in G1. Okay, then we also remove B, is it? After removing B from the graph, let's see what the GYS after removing B, okay? If you take a look, after we removing B, then A, we don't have B, C, we don't have D, E, is it? And B is also gone, okay? Yeah, so that's so it did achieve the goal, okay, after removing B. And then you check if B and D relationship stays and all vertices. So similar. And we also have the second graph. Second graph is from textbook figure 22, 3, okay. And pretty similar, we create of the vertex and the edges, then we do the similar operation, okay? And the output, that's also in our diagram, okay? It's also in the running result. It's also provided here. Okay, so that's for this example, and we are going to discuss the next example in our next lecture. See you.